Okay, so given the linear correlation coefficient r, and just in case this is the first time you're hearing about r is a number that tells us how closely two columns of numbers fit a straight line. So this would be an r, like see how the scatter plot is fitting a really tight line? This is an r of about like 0.9. Okay, and this would be an r of exactly 1. And then this would be an r of like 0.4. So hopefully you're getting the idea here. The closer we get to the number 1 for our correlation coefficient, the closer it makes a straight line. And you can also have negative r. This is r equals -1, because it's a perfect negative line. As you move to the right on the x-axis, you go down on the y-axis. So it's decreasing as we read the graph from left to right. So that's r. That's the basics. Just like when you have t or z test statistics, you want to look up a table value so you can compare them and see if you have enough statistical evidence. So this is a decent sized r for our data set. It's not 1, but it's definitely something bigger than 0. Is it significant enough so we can say there's some sort of correlation? Well, we need to compare it to the table value, or critical value. Okay, so before you do that, just know the degrees of freedom isn't n-1 like it used to be with our t-tests for means. It's n-2. Okay, so our degrees of freedom is 23 for this problem. Okay, so in the back of your book, I think there's a table for critical values of r, but I think it's way quicker. It's just pulling up numbers from a table, saving us the work of having to do the calculus to find the area under the curve. So find it however is easiest for you. Like I'm trying right now. I'm trying to pull up a web browser. That's the quickest way for me to find critical values. There we go. So if I go to Google, r is the correlation coefficient, but I think if you type r critical value calculator, yeah, the first one that comes up here, watch out because it's actually showing you a bunch. You want to scroll down to r. Usually it's lowercase r. Now this tail part, let's go back to our problem. This is a two-tailed problem if you read through it, because they don't specify, like they think it's a positive or negative correlation. A positive correlation, you'd be looking at like a one-tailed test. You're trying to find the probability of it being greater than your test statistic. That'd be for a p-value. The probability of surpassing your test statistic. Or if it's at a negative correlation, then you're talking about a left-tailed test. So since it's got these plus or minus symbols, we know we've got a two-tailed test. Okay, and the significance level is 0.05. That means you got to split up that area evenly between these two critical values. Between these two tails, I should say, 0.025 and 0.025. Okay, because if you add those together, that makes your significance level of 0.05. So in this table, I'm not going to type 0.05. I'm going to select 0.025. Then 23 for degrees of freedom. You calculate, and there's our critical value, 0.396. Almost ready to answer the question. There we go. Critical value is 0.396, so it's one of these two. Is it significant? We are going to circle this one. That yes, it's significant because it's our value. I'm having trouble saying both of those at the same time. Our test statistic, r equals 0.543, is bigger than the critical value. So we're over here, and this is the critical value cutoff. We're beyond it. We have significant evidence. It does look like there's a positive correlation. So yes, there is a significant linear correlation.